This is Abdelatif,
And I'm Bronson.
and this is Lab 10 Lasers.
So this is the ESA experiment, where our setup includes our laser under experiment, a mirror, and our detector setup. And the purpose of this is to analyze the different existing transverse and longitudinal modes within a laser cavity. Systems we are comparing are the RF photodetector and the Fabry-Perot. We expect the photodetector to not operate fast enough to follow the different optical frequencies present. So the detector will average the two frequencies, creating two different peaks. One peak in which is a difference term, and the other in which is a summing term.
For the first part of this experiment, we will measure the length of the laser. Using that length L, we can find the FSR, and using the speed of light. With this, we found an FSR of 487.5 megahertz. We expect this FSR to be smaller than the actual value because the actual cavity inside the laser is smaller than the total length. Using our Fabry-Perot and the oscilloscope, we can find the distances between the peaks. Using those distances, we can find our FSR, which will then give us the actual size of our cavity. The same can be done with the photodiode and the RF analyzer. These values make sense because the cavity inside the laser should actually be smaller than the distance. The laser is emitting S-polarized light because if we change this axis, we can see a change in the oscilloscope.
This is the laser alignment experiment where we have an HENE source, and the purpose of this is to actually make it laser using this cavity length, a mirror, and an output coupler, and then another HENE laser to align it.
This is slanted so that only P light travels through it. By calculating the Brewster's angle, we can find what angle this mirror is slanted at.
When exploring higher order transverse modes, we can expect the intensity distribution to look of Hermite-Gaussian functions. And you can see that it's dependent on our transverse and longitudinal mode numbers as well as our curvatures of our mirrors. The Fabry-Perot etalon consists of two plane parable mirrors at a distance L. Changing this distance L will effectively change the interference between the reflections of the plates. The resonant frequency of the Fabry-Perot will match the laser cavity frequency when constructive interference occurs between the transmitted beams. They're in phase. By measuring and plotting different points along our z-axis far away from our laser, we can fit it linearly to get the divergence angle and the location of our beam radius.
The detector reads the laser light into the computer.